In a world full of calculus exams, this is one of them. And more particularly, this is from Calculus 2 and Exam 2. So now we're talking about techniques of integration, trying to get into some of those more interesting, more flavorful integration problems. How do we actually go about solving them? So a little bit about, integration by parts, trig substitution, trig integrals, partial fractions. It's going to be a blast, a fun ride ahead of us. 6 problems. This was when we had long answer problems, so lots for us to do. But of course, before we do anything, always remember to write your name, because if we don't put our name, we won't get the credit. All right, let's begin. The first problem. Find the integral x to the fourth log of x quantity squared dx. Okay, all right. So we look at this problem and say, well, we know some things it's definitely not. It's not partial fractions. There's no polynomial or polynomial. It's not trig substitution. There's no square root. It's not a trig integral. There's no trig. And it's not an improper integral because it's indefinite. And so okay, well, there's not a lot of things left on our list. By process of elimination, integration by parts. But actually, even without doing process of elimination, integration by parts is a very reasonable, logical choice. Because what do we have? Well, we really have 2 things multiplying together, and that's sometimes a hint. Now, that's not automatic, but more to the point, one of these pieces, we look and say, I do not want to integrate that. But I am willing to differentiate it. So oftentimes, if you do see something that says, I don't want to integrate you, but I am willing to differentiate you, and the derivative should be somewhat nicer, that's a good sign of integration by parts. And so we say, okay, so we said that's the part we don't want to integrate, so that becomes our u. This x to the fourth dx, well, that's the other part, that's our dv. So let's make some notes here. If u is log of x quantity squared, be careful here. I know what you're thinking. Hey, log, can't we bring that 2 down? No, because where's the square? It's outside of the log. It's not inside of the log, so be careful, be careful. Well, then the derivative, okay, so log squared. So it's a function log inside the square function. Chain rule this. The 2 comes down times log of x to the first power times the derivative of log of x, which is 1 over x dx. All right, now what about our dv? Well, that's x to the fourth dx. And the integral of x to the fourth, well, add 1 to the power, x to the fifth, and divide by that new power, 1/5, x to the fifth. Okay, so that tells us that this is going to be equal to uv. So 1/5 times x to the fifth times log of x squared minus the integral v du. So minus the integral, and if we multiply these together, well, we have a 2/5. All right, so we'll write that down. And then we have x to the fifth and a 1 over x. That's x to the fourth. And then we have a log x times a log of x dx. All right, progress. Maybe. Now, how do we know if it's progress? Well, the basic rule of thumb is to say, is something simpler than before? Now, the constants, we can move those in and out, so don't worry about that. X to the fourth looks pretty much the same. But notice this log of x. Originally it was squared. Now it's not. Simpler. Ha ha ha! We did a good thing. All right. Well, so what do? It's the idea so nice, we'll do it twice. So you can do integration by parts multiple times. Now, again, same philosophy. And in fact, there's a rule of thumb that says, look, if you made a decision, you've got to be consistent if you apply the rule over and over. So we made a decision to use that log as our u. So it's that log part needs to keep staying as our u. if we flip and change our mind, we'll undo all the good work we did. We don't want that. We want to make progress. All right, so here's our u, and the 2/5 x to the 4th dx. We'll make that be our dv. Okay, so now let's make some notes here. We have u is log of x. So now the derivative of this, more straightforward, 1 over x dx. dv, well, that's 2/5 x to the 4th dx. And so what do? Well, you add 1 to the power, so that becomes x to the 5th, divided by the power. So you already have a 2/5. You're going to divide by 5 again, so that makes a 2 over 25. All right. So this equals, now we're coming down here, so we'll put a little arrow here just to make sure we followed it down. Don't forget this term, 1/5 x to the 5th log of x quantity squared minus, and now here's a good piece of advice. When you have that minus sign, throw in some parentheses. Parentheses will help you make sure you get that minus sign distributed correctly. And or if there had been a constant here, again, put parentheses. Parentheses are helping you save points because they help you remember how to appropriately distribute terms. Okay, so what do we have? We have uv. So we can write that as 2 over 25 x to the 5th log of x. Okay, uv minus the integral of v du. Well, we have that 2 over 25, and x to the 5th times 1 over x is x to the 4th. And, whoops, I should make my parentheses the same color, just to emphasize. That's a red parentheses. There we go. Ha ha. And that minus will distribute through. Okay, so we're in the home stretch. So what do we have? Well, we'll swap colors one last time as we write our answer. We have ourselves our 1/5 x to the 5th log of x quantity squared minus 2 over 25 x to the 5th log of x. Right? Minus minus plus. Now here we integrate. Integral of x to the 4th, we've done that. That's x to the 5th. And we're going to divide by 5. Well, there's already a 25. Multiply that by 5. That gives us a 2 over 125. And don't forget, plus c. That's right. If you have an indefinite integral, you need that constant at the end. If you forget it, you'll lose a point. We don't want to lose a point. We want all our points. All right. Well, great. So integration by parts. Wonderful tool. Often very useful if you have things multiplying together and one part that looks terrible. Be ready to integrate by parts multiple times and make sure you distribute properly because it's easy to forget things. And don't forget the c. It's sometimes very easy to forget the c. All right. We've got lots of problems, so let's keep going. Number 2. Evaluate the following integrals. And they don't seem to have much to do with each other, so we'll do them separately. So part A, the integral of secant to the 9x tangent cubed x dx. Now, whenever we have an integral with secants and tangents, we always do sort of the following check, and which is to say the following. We're going to think of it as two possibilities. One thing we can do is we can pull a secant squared off to the end. So if we did that, this would look like secant to the 7th x tangent cubed x times secant squared x dx. The other thing is we can pull a secant x tangent x off to the end. And if we were to do that, well, we would have secant to the 8x tangent squared x times secant x tangent x dx. And you're saying, okay, what? Why are you doing this? Well, because there's two good potential substitutions. One potential substitution is to say, hey, if I were to set u equal tangent x, then this secant squared x dx would be du. Another could be, well, if I set u equals secant x, then secant x tangent x dx would be du. So now we come to the question, which road do you want to take? Well, you might say, neither is good. See, you want to put tangents, but that has secants. Here you want to put secants, but that has tangents. Now, here's the cool thing. There's this lovely fact, and we'll write it down, and it says, if you take tangent squared plus 1, that's equal to secant squared. Now, what that tells us is the following. If I have a secant squared, I can swap it for a tangent squared. Yes, I have a plus 1, but I can basically swap squares of secants for squares of tangents, but also vice versa. If I have a tangent squared, I can swap it for a secant squared. Yeah, there's minus 1, but don't worry about that. So secant squareds and tangent squareds can be swapped in some way. So the key is to look at the powers. And as we look at our powers, we say, well, if I were to substitute tangents, I'd have to rewrite my secants. Notice that's 7. That's odd. Not going to work. If I come down here and say, well, if I write my things in terms of secants, I got to replace my tangents. And we say, oh, that's 2. Even that can work. So now what have we done? Well, we said, okay, we have 2 possibilities, and this road will not work, but this one is going to be great. So what do we have? Well, keeping going in the same direction, we say the secant to the 8 we like, so we leave it there. Secant to the 8x. The tangent squared x we replace. And here, notice that we can replace tangent squared by secant squared minus 1. And then we have our secant x tangent x dx. And we're ready to do the substitution. U equals secant x, du equals secant x tangent x dx. And if we do that substitution, what do we have? Well, we get the following. This becomes our integral of u to the 8th times u squared minus 1 du. And this is nice. We can distribute the u to the 8th through, so this becomes the integral u to the 10th minus u to the 8th. And these are integrals we can do. So this becomes equal to, so we're just going to give ourselves space since we have it now. We add 1 to the power divide. So 1 over 11, u to the 11. And then add 1 to the power divide. Minus 1 over 9, u to the 9. And don't forget plus c. Oh wait, we're not done. These are u's. We didn't start with u's, we started with x's. Because it's indefinite, we need to get back to x. And that's okay. We know that u equals secant x. So we say, all right, well, hey, this is 1 over 11 secant to the 11th power x minus 1 over 9 secant to the 9th power x, and toss in a plus c, and life is good. There we go. That's part A. Now on to part B. So, part B. Integrate sine squared x cosine squared x dx. So now we have not secants and tangents, we have sines and cosines. Now what do you do when you see sines and cosines? Well, you're going to focus on the powers. Now in this case, our powers are both 2's. Say, okay, so we see a lot of 2's going on here. That means everything's even. If one of them had been odd, we'd be like, woohoo! Because we could pull the term off to the end, and life would be good, a substitution, and it would fall very much like part A. But we don't have that. So what happens if everything's even? Power reduction. And there are 3 power reduction identities. You might say, wait, you mean 2? No. I mean 3. So let's write them down. So cosine squared x is equal to 1/2 1 plus cosine 2x. So we call it power reduction because you go from a square something without a square, less power. Sine squared x, that's 1/2 1 minus cosine 2x. And now the last one, which personally for me is my favorite, sine x cosine x is 1/2 sine 2x. I call it power reduction because here's two terms, here's just one. Now, is it right for us to have favorites when it comes to trig identities? Well, that's a great philosophical question, but in this case the answer is absolutely. This is our favorite one. We prefer this one. And you might look at that and say, why would we prefer that one? Well, notice, what does this have, or rather, what does it not have compared to those? See these pluses and minuses? That means more algebra. You got to do distribution and stuff. More algebra leads to potentially harder computations. So be nice to yourself. Remember, we love ourselves. We want ourselves to succeed. So give yourself the easiest road to travel. Because when you do some of these problems, there's kind of options that you have. You can choose to make it harder or not. Choose to not. And I hope this doesn't come as a big like, what? We should choose to be nice to ourselves? Yes, you're wonderful. I like you. I like you the way you are, and I want you to do well. Okay, so here's how we're going to proceed. We looked and say, let's use this one as much as possible. And it's not going to be hard in our case. Because we say, well, really, this integral is sine x cosine x squared. So I say, all right, well, let's use this nice power reduction. That's 1/2 sine of 2x squared dx. Or we would normally write this as 1/4 sine squared of 2x. Okay, cool. Notice here I have essentially 4 functions, because there's 2 sines, 2 cosines. Here I'm down to 2, so that's why it's reducing. Now how do we do sine squared? Well, okay, again, look at the power. And what do you notice? It's still even. So what do? Power reduction. We can't use that one, but we can use this one. So we say, okay, so this is integral 1/4, and then we have 1/2 times 1 minus cosine. And this is the part where I have made mistakes in the past. So I always say, slow down, Steve. Don't make that mistake again. When you're doing power reduction, you double the angle you currently have. So it's not necessarily going to be 2x, it's going to be double what you currently have. What do we currently have? 2x. What's double 2x? That's what goes there. So double 2x is 4x. 4x. So make sure you put the right term there. Well, all right, so you have a 1/8. You can throw that in the front. And now the integral of 1 is x. Integral of cosine is sine. Still going to be a minus in front. And leave yourself a little bit of room, because you almost always have to account for a constant on the inside. The way we account for that constant is we divide by that constant. So 1/4. And of course, it's indefinite. Don't forget your plus c. That's a great answer, but I'm going to go ahead and distribute the 1/8 through. So 1/8 x minus 1/32 sine of 4x plus c. Now, here we could go and try to rewrite it in other ways. We could, for example, say, here's sine to the 4x. I can get it back to sine x and cosine x. But you don't have to. The only thing you have to make sure of is that it's compatible in the sense of the variables used. So we started with x's, we've ended with x's. Nice! Life is good. But if we start with x's and end with u's, not going to work. So it's okay that we have sine of 4x here, but we have sine of x and cosine x there. That's okay. The important thing is that we have the x's. We have our x's. All right, well, that was fun. 2 down. Got a lot more to go. So let's keep moving right along. All right, to number 3. Solve the integral of 2x cubed plus 2x minus 1 divided by x to the 4th plus x squared. We don't have to guess a lot what we're going to be doing here. we say, hey, polynomial upstairs, polynomial downstairs. This is what we call a rational function. And so when you see polynomial upstairs, polynomial downstairs, rational function, we say, this is going to be a partial fractions problem. Okay, so we know where we're going. Partial fractions. Now there's a step 0. We almost never have to do this next thing, but we have to check for it. And step 0 is long division. And what you do is you say, look at the highest power upstairs, look at the highest power downstairs, and compare. Highest power upstairs, 3. Downstairs, 4. This is good. We want the downstairs to be higher. And as long as it's higher, doesn't matter by how much, then we're good to go. Okay, so no long division needed. All right, long division done. Check. Next step is we need to factor x to the 4th plus x squared into pieces. And they need to be nice pieces. We call them linear and irreducible quadratics. And oftentimes they'll just hand the factorization to us if it's tricky, or if they don't, it means it's like kind of pretty clear how to factor. And looking at the x to the 4th plus x squared, there's something that seems pretty clear on how to factor, namely, you can pull an x squared out. All right, so don't bother doing anything with the upstairs, but do factor the downstairs. Even if it looks very tempting to do stuff upstairs, it's not worth our time. So x squared times x squared plus 1. And this x squared plus 1 is one of those irreducible quadratics, in the sense you can't really do anything to it. You can't factor it further, because otherwise you'd be very complex. Okay, so yeah, when it comes to factoring, that's as good as we can get. All right, no worries. Now that's our next step. Cool. Okay, so we're going to now do some work. In fact, we really should pull this to the side. And I should have started pulling it to the side earlier. Well, let's pull it to the side. So we have this 2x cubed plus 2x minus 1 over x squared times x squared plus 1. And here is the important thing. And probably this is the easiest place to make a mistake. And so it's really important that you make sure you get this right. We need to say, how do we pull this apart? And we don't have to get it exactly right, but we do need to get the form exactly right. So you start looking at your pieces. And you say, well, I have an x squared. Now you really should think of this as x to the power square. So x is your piece, but it's repeated. It's a repeated piece. So when we start writing it down, we say, well, I need to start with my powers of x, and I have to go up to x squared. All right, so x, you can think of this as really like x to the power 1, x to the power 2. We're building up. Now, that's that part. And on the other hand, you have this x squared plus 1. Okay, so that's going to be a piece. And there's just one of them, so there's an x squared plus 1. And now, the important thing. What goes upstairs? Well, that's what we're trying to find out. That's the whole point here of what we're doing. So we're trying to figure out what goes upstairs. And so when I have things like linear terms, I put constants. So a and x. Now, don't think of it as x squared. Think of it as x. Focus on the inside part. And here, this is irreducible quadratic. So I'm going to have two things upstairs, cx plus d. Now, there's always a quick sanity check, and here it is. How many unknowns do we have? A, B, C, D. 4. 4 unknowns. What's the degree of the denominator? 4. Those should match. If they don't match, mistakes were made. And say, okay, whoa, they're not matching. Let me find my mistake. All right, so now comes the next step. And this is the most important step. We need to solve for A, B, C, D. Essentially, we don't know what they are, but we want to know them. Oh, that's nice. It's good to get to know things better. So we look at it and say, well, we don't like fractions. I know. I'd really have a hard time with fractions. I've made so many mistakes over the years with fractions. I get to the point where it's like, if I can get rid of them, I do get rid of them. So we get rid of them by using the fraction denominator here of the original term. So I say, well, I have an x squared and an x squared plus 1. So I'm going to multiply everything on both sides by that term, which will clear out the denominator, 2x cubed plus 2x minus 1. And now we have here, that's equal to a. And if I multiply here, I get 1x to cancel, so it's x times x squared plus 1. Here, both x's cancel, so it's b times x squared plus 1. And then on the last term, the x squared plus 1 cancels, so it's cx plus dx squared. All right, good. Now, I always like, if I can, to make some good choices. And I can see at least one good choice. X equals 0. Okay, so by making a good choice, we say, look, these two sides have to be equal to each other. That's got to be true for all values of x. So let's plug in a specific value for x. And if you do that, you get negative 1 equals a times 0, goes away, plus b times 1, which is b, plus c times 0 plus d times 0. And I say, aha, we get one of our values. B equals negative 1. And so let's update up here. So this part is negative 1. All right. Now, how do we get the rest? Well, unfortunately, there's no other great choice. There are some choices that you could make. You could be very creative and go with I. I strongly discourage that. Strongly discourage that. Don't be creative. So if you've run out of good choices, there's a couple of options. Plug in some random numbers, and you get to a series of equations unknowns, or compare coefficients. So let's take this right-hand side and expand it out. Okay, suppose we did that, and we have the technology. So we would have ax cubed plus ax, all right, we'll distribute that out, plus bx squared plus b, and yes, we can replace the b with negative 1, we should have done that, and plus cx cubed plus dx squared. Okay, so just distribute. And now you get into your hunter-gatherer. Okay, let's look for powers. X cubed, we have an a plus a c, x cubed. Okay, so let's make sure. I'm just gonna mark things when I've accounted for them. All right, how about x squared? All right, we have a b and a d. So plus b plus d x squared. Okay, good. That accounts for those terms. How about x? There's just one of them. Plus a times x. Cool. And how about the b? Well, there's just the b. And remember, this is 2x cubed plus 2x minus 1. And now we say, look, two polynomials have to be the same if and only if their coefficients are the same. So we say, well, look at the constant terms. Minus 1 must be b. All right, that says b equals minus 1. It's not surprising, actually. The constant terms are what you get when you plug in 0. So, all right, no big surprises there. Now look at the coefficient for x. 2 has to be a. Oh, well, that's new. Okay, so let's make sure we're writing this down. b equals negative 1, a equals 2. All right, well, what about this x squared term? There's no x squared term here. So what does that tell us about this x squared term? Well, that x squared term has to equal 0, because otherwise there'd be an x squared term there. So we get, oh, b plus d equals 0. But wait a second, we know b. So d is negative b, which is negative 1, which is positive 1. And now the last is the cube coefficients. So 2 has to match with a plus c. So a plus c has to equal 2. But wait, we know a equals 2. So if a equals 2, what does that tell us? Well, that tells us that c equals 2 minus a equals 0. Now let's update. so remember, we have to update things as we go. A is 2. C is 0. And D is 1. Okay, so I'm going to pause for a second here and say, when it comes to doing partial fractions problems, 2 of the most common mistakes are getting the right form, and you do all the work and you get these values, but then you forget to put them in. Don't forget to put them in. You worked hard on this. You deserve the points. So make sure you account for every value and update it correctly. Don't like, I'll put a 1 here and a 0 here. No. Do exactly what it should have. Okay. All right. Now, all of that is our partial fractions work. That's our algebra to the side, which allows us to jump back to our original problem and say, well, hey, we can now take this expression and replace it with this expression. So we have what? 2 over x minus 1 over x squared plus 1 over x squared plus 1 dx. Right? I'm just taking this, but plugging in the numbers. 2 over x minus 1 over x squared, 0x plus 1 over x squared plus 1. And now we just integrate. And on a side note, don't forget this really means x to the negative 2. So integral of 2 over x, 2 log x. Integral of x to negative 2, well, you would add 1 to the power, making x to negative 1, divide by negative 1, and so that makes it really a plus x negative 1 or plus 1 over x, and plus 1 over x squared plus 1, it brings the tear to the eye, doesn't it? Arctangent. Beautiful function. And don't forget, of course, your plus c, because after all, we want all the points. And there we go. There we go. Our partial fractions problem worked out. Whew, what a fun one. What a great ride. All right, we're halfway done, but that still means we've got a lot of fun stuff to do. Number 3. Number 4. Oh, yes. Number 4. Consider the integral. Integral 0 to 2 sine pi x squared dx. Using the trapezoid rule with n equals 4, approximate the value of this integral. Simplify so that no trigonometric functions appear. Okay. Well, we have to make sure we understand what this n equals 4 is referring to. So when we talk about n equals 4, that's the number of intervals. So we're saying we have this function. Here we have our f of x, and we're going on an interval. So here's our interval. We're going from 0 to 2. So we're going to take our 0 to 2, and we want to split it up into 4 equal pieces. And so we have halfway in between is 1, halfway in between that is a half, and halfway there is 3 halves. All right, 0, a half, 1, 3 halves, 2. All right, so there's our setup. Now, so you might notice, wait, you have 5 points. Yes, 5 points, 4 intervals. So don't try to get 4 points, and because that would lead you to something that would be a headache. Okay, what do we need to know? Well, what we need to know is what is the function doing at each of these points. So we're going to make some notes here. And, we have f at 0, that's sine of pi times 0, and sine of 0 is 0. Very convenient. F at a half, that's sine of pi times a half squared, that's a fourth. And now, well, we know it, or we can look it up, hopefully. Sine of pi fourths is square root of 2 over 2. Cool. F of 1, that's sine of pi times 1, sine of pi, and sine of pi is 0. All right, f of 3 halves, that's sine of pi times 9 fourths. Now you might say, well, wait, 9 fourths pi, where is that? Well, actually, if you think about the unit circle, right? So this is pi force coming out here at 45 degrees. Now 9 pi force is 8 pi force, or 1 revolution around is 8 pi force plus pi force. So this is the same angle as pi force. So sine of 9 pi force is the same value, root 2 over 2. And the last thing we need is f of 2. So that's sine of 4 pi, and that's 0. Okay, so good. So we can go ahead and mark it on top of here. 0, root 2 over 2, 0, root 2 over 2, 0. Okay, now, how does the trapezoid rule look? Here's how I remember the trapezoid rule. It's delta x over 2, and then you have this pattern 1, 2, 2, 2, 1. And what we interpret this as, delta x is our width. So come up here, what's the width of our interval? It is a half. So we're going to have 1/2 divided by 2. So that becomes 1/4. Now these numbers are our coefficients. So just to drive it home, I'm going to be very slow and say this is 1 times f of 0 plus 2 times f of 1/2 plus 2f of 1 plus 2f of 3/2 plus f of 2. Okay. And 1 times f of 2. And so if I were very clever, I would have prepared better. So 1, 2, 2, 2, 1. Right? These coefficients. And the delta x over 2 is 1/4. Well, we're almost there. We're in the home stretch. What do we need to do? We need to evaluate. So we have 1/4, 0, plus square root of 2 over 2 times 2, which is square root of 2, plus 0, 2 times 0, plus 2 times root 2 over 2, square root of 2, plus 1 times 0, which is 0. So we have 2 square root of 2 times 1/4, and so what does that turn out to be? Well, that turns out to be square root of 2 over 2. All right, so there we go. That's the answer to part A. Part B. Now approximate this integral using Simpson's rule. Once again, assume that n equals 4. Simplify so that no trigonometric functions appear. And so we're like, oh, we've done all the work. We have the data. So all we have to do is write down the formula for Simpson's. Now that has a different pattern. That's delta x over 3. And now the pattern is 1, 4, 2, 4, 1. So that will become delta x is still a half. It's the length between 2 points. So delta x over 3 is 1 over 6. And then we have our, and let me see if I can do it better this time, our 1 times f of 0 plus 4 times f of 1/2 plus 2 times our f of 1 plus 4 f of 3/2 plus 1 times f of 2. Okay, so again we have delta x over 3, and we have our 1, 4, 2, 4, 1. It's not like we treat all data equally. We give some data a little bit more weight. And by doing that, we can get a little bit more accurate in our approximation. So, last thing is plug in our values. Well, this is going to be 1, 6. F of 0, still 0. Then we have 4 times root 2 over 2, which makes that 2 root 2. F of 1, still 0. 4 times f of 3/2, so 4 times root 2 over 2 is 2 root 2, and f of 2 is 0. Well, the zeros, of course, don't matter. We get 4 root 2 over 6. I almost made it fit. 4 root 2 over 6, there we go. And then you can just sort of cancel a 2, so that gives us a 2/3 square root of 2. And that's our answer. All right, there we go. And great. So this is a very, in some sense, numerical integration. You just need to know the rules. Trapezoid rule, Simpson's rule. How do the coefficients work? How do you weight things? And then make sure to have the right term in the front. Other than that, it's not so bad. Not so bad. All right, let's keep going. Number 5. Evaluate the integral or show that it diverges. Now we might say, well, why might we think diverges? The only time when we ever have anything diverging is if it's improper. So we say, oh, the fact that we even have the potential for diverges, this tells us we're in the improper integral area. All right, so let's look at this integral. Is there anything that would make this improper? So we tend to say, is there anything causing it to blow up, an asymptote, vertical asymptote, or a horizontal asymptote, which has an infinity involved? The downstairs is nice. Great kind of thing. So we look at the upstairs and say, there's an infinity involved. So it's improper because of that part. All right, so let's go ahead and work through this. Now, we're going to actually do this 2 ways. So let's talk about the first method, which is just like, let's go for it. Method 1. Okay, so we say, look, this integral, 1 to infinity of x divided by 4x squared plus 1 dx is equal to the limit as b goes to infinity and integral 1 to b of x over 4x squared plus 1 dx. All right, now, what's going to happen here? Well, we now work to integrate it. And here, sometimes we say, well, let's just do an indefinite integral on the side and come back in. Sometimes we can just do it right away and say, well, what does it kind of look like? If there wasn't a one, if there was a 1 upstairs, what would we say? It feels arctangent-y. We've already had 2 arctangents on this exam. Could we be lucky enough to have 3? No, we're not that lucky. But we say, well, okay, hold on, maybe there's something else. 4x squared plus 1. What's the derivative of that? It's like 8x. That's like x. I'm like, what? That's amazing. Okay, so we say, okay, cool. What we can do is say, all right, given that that's true, we can do a substitution. We'll let u equal 4x squared plus 1, and then du will become 8x dx. Or, using our fancy pens, 1/8 du is x dx. Okay, so what do we have? Well, this is the limit as b goes to infinity of the integral. And here, the x dx is going to become a 1/8 du. And then this 4x squared plus 1 downstairs is a 1 over u. And the bounds, the lower bound, plug in 1. 4 times 1 plus 1, 5. Plug in b, that's 4b squared plus 1. Okay, now the 1/8, that's constant, don't worry about that. What's the integral of 1 over u? Well, that we can do, that's log. So this is the limit as b goes to infinity of 1/8 log of u. Evaluate that from 5 to 4b squared plus 1. And we say, well, hey, that's the limit as b goes to infinity of 1/8 log of 4b squared plus 1. And then subtract 1/8 log 5. Now, because this is a constant, we can really separate out it from the limit. So the real question is what happens here. And now our great our great ugh. The inside is getting big. 4b squared plus 1 gets big. What happens to log as you head off to infinity? It gets big. It doesn't want to. It drags its heel, says, I don't want to go to infinity. But it goes. It goes. And so it's going to blow up. So this part goes to infinity. Now you might say, wait, what about the 1/8? 1/8 times a big thing is still big, going to infinity. So we say, this is infinity, or it diverges. Okay. So that's our answer. All right, that's method 1. Okay, let's talk method 2. And I think in the solutions, it only talks method 1. And so I want to talk method 2 because there's a second way to do this, which is fun. Which is to say, before you even start this, you should know the answer of whether it converges or diverges just by looking at it. Okay, so what do we say? Well, converging, diverging says look at the rate of growth. And so we look at x over 4x squared plus 1 and we say, okay, how does it behave? Well, let's answer that by saying get rid of the lower order terms. And upstairs we say, well, there's only one term, so we don't have lower order terms. Downstairs we say, oh, well, there's 4x squared and there's 1. Well, 1 is small. It has no effect of, when you have 4x squared and x is 1,000,000, 4 times 1,000,000 squared versus 1, insignificant. So you say, really what's happening is that for large x, this is approximately x over 4x squared, or if you like, 1 over 4x. So that's the growth, or if you prefer, decay. That's how quickly it's going to 0. Now, what's true? Well, what can we say about the integral of 1 over 4x? And the answer is the integral of 1 over 4x dx diverges because, all right, I'm going to move this up so I can make notes. Integral 1 over x to the p will converge if and only if p is greater than 1. And notice here, this is p equals 1. And so we say, aha. So you say, great. So what does that tell us? Well, it tells us that 1 over 4x diverges. But asymptotically, these are the same. So in other words, if you think of this as f of x, and this as g of x, we have the limit as x goes to infinity, f of x over g of x is 1, because we just took out the lower order terms, so it doesn't change their limits as you head to infinity. They approach the 0 the same way. So what does all of this tell us? Well, it says these grow in the same way. This diverges because we can compare it to an integral where we know whether or not it converges. So if this integral diverges, that integral diverges. And how do we write that down? Well, by the following. So by the limit comparison test for integrals with we'll say f of x or g of x, equals 1 over 4x, the integral diverges. So oftentimes you can know before you even start whether something is convergent or divergent. It all comes down to how quickly do you grow. If you grow, or I keep saying the word grow, how quickly do you go to 0? If you go to 0 very slowly, diverge. If you go to 0 quickly, converge. So it comes down to your growth. How quickly do you grow? All right, last problem. Number 6. Consider the region R enclosed by y equals x over 4 minus x squared to the 3/4, the line x equals 1, and the x-axis. Hey, they gave us a picture. Nice. The region is revolved about the x-axis to form a solid. All right, they're giving us a solid. Boom, give us a solid, yeah. Find the volume of the solid. Your final answer should not contain unevaluated trig functions. Okay, now they kind of gave away the game here. Notice they said trig. What do we not see right now? We don't see any trig. So it's like, wait, what? How could there be trig in our answers? And like, oh, you want us to get to trig. That means we somehow have to get trig involved. So this is actually a clue that says trig substitution. And we're like, nice. Okay, so now we know what's going on. Sometimes they're very blatant about it. Sometimes they're subtle. Sometimes they don't even give us any clue at all. But we'll always take what they are willing to give us. Okay, so we say, let's look at our situation. Now, we're given this as a function of x. So we're going to integrate with respect to x, which means that we slice our little pieces. And we say, okay, so that's what a typical little piece looks like. Now, if we spin this little piece, what shape gets formed? Well, the answer is we form a circle. And so we say, oh, so this is the disk method or the washer method. Okay, so now we say we're going to use washer method. And disk method is a washer without a hole in the middle. Okay, so, well, what does our basic formula say? It says our volume is you add up from A to B, pi, your radius squared. Your inner radius is 0, so I'm not going to do the whole expression. And then you have your width. Okay, so for us, we're going from, in the x direction, 0 to 1. We have pi. And then our radius is the height. So it's this expression, x divided by 4 minus x squared to the 3/4 squared. And our width is dx. Okay, so now we have our setup. And if we multiply that a little bit more, we get 0 to 1 of pi x squared over 4 minus x squared to the 3/2 dx. Okay, now we say, great, that's the integral we have to do. And we see, yeah, trig substitution does make sense. Not that we're just inferring it, but notice you have this little over 2 there. That's indicating a square root. And we say, oh, that's the square root where there's a plus or minus on the inside. That's almost always a sign of trig substitution. So let's remind ourselves really quickly the situations you might find yourselves in. If you see square root a squared plus u squared, well, that's a substitution. U equals a tangent theta. If you find yourself in a situation u squared subtract a squared, that's the secant. You're like, Steve, you're delaying. Yes. A squared minus u squared, that's sine. Now, we have number squared minus function squared. That's this scenario. So in particular, we see 2 squared minus x squared, because I'm going to write it as a square. So 4 becomes 2 squared. So that tells us our substitution, u is x, and a is 2. So x equals 2 sine theta. Now we make some notes here. We're going to say that dx, derivative of sine, is cosine. Okay, that's good to know. And then, of course, the other thing is to say, well, why did we make this substitution? It's to help us with this square root. If we plug in x equals 2 sine theta, this becomes square root of 4 minus 4 sine squared theta. Well, we can pull out the square root. You can pull 4 out, and that becomes a 2. Then you have 1 minus sine squared, which is cosine squared. So it's really 2 cosine theta. Okay, so there's our sort of guide for our trig sub. So we carry that out. And we get this is equal to the integral. We have a pi, and we have an x squared. So that's 2 sine theta squared. We have a dx, which is 2 cosine theta d theta. Then downstairs we have 4 minus x squared to 3/2. So that's like the square root of 4 minus x squared cubed. So that's 2 cosine theta cubed. We still need to do one more thing. The bounds. Be careful with the bounds. You got to update the bounds, right? These bounds that we had written down were x bounds. So it's x equals 0 to x equals 1. And we want to go to from theta equals something to theta equals something. So let's do our bounds really quickly. So move this up, give ourselves more space. And all right, so we plug in our x is 0. So 0 equals 2 sine theta. Well, that tells us that sine theta equals 0. So that happens at 0. Okay, so 0 became 0. It happens. What about the 1? 1 equals 2 sine theta. Well, that tells us sine theta equals 1/2. And we say, oh, well, that's, what angle is that? And we can look it up, or we know it. And we say, well, that happens at the angle pi over 6, or if you like, 30 degrees. So pi 6. All right, well, let's see what we have. First off, we have lots of 2's. There's 2 squared with another 2, so that makes 3 2's upstairs, 3 2's downstairs. So all the 2's cancel. Nice. And we'll go ahead and mark that. Farewell, 2's, you are gone. Waha! And what do we have? Well, 0 to pi over 6. We have a sine squared upstairs, a cosine left, and a cosine cubed. So wait a second. We see cosines both upstairs and downstairs, so we'll cancel. So that gets us to sine squared over cosine squared. Now, is there a way to handle sine squared over cosine squared? Well, that's like tangent squared. Oh, nice. So this is integral 0 to pi over 6, tangent squared theta d theta. Now, is there a way to handle tangent squared? Well, what you can do is you can swap out, because there's a rule that says like tangent squared is like secant squared. And remember our nice trig identity. Tangent squared plus 1 equals secant squared. So this really becomes integral 0 to pi over 6. And you know what? I can see I already forgot to write the pi. Don't forget to write stuff. It's easy to forget. Pi, and then tangent squared becomes secant squared minus 1. We're in the home stretch. So the integral becomes pi. Tangent, right? The integral of secant squared is tangent, because the derivative of tangent is secant squared. Okay, so we have tangent theta and minus theta. Evaluate from 0 to pi over 6. Now, good news. When you plug in 0, tangent of 0 is 0 and 0 is 0. Nice! So the last thing for us to do is to plug in, and we have to plug in pi over 6. And then we'll be done. Okay, so we have, this will be equal to pi, tangent of pi over 6, and minus pi over 6. And we say, okay, all you need to know is tangent of pi over 6. Well, you can learn the formula, or I should say learn the table, or hopefully you can look it up. Tangent of pi over 6 is root 3 over 3. So we end up with pi times root 3 over 3 minus pi over 6. And there we go. The last answer, the last problem, and we made it. We finished it with time to spare. All right, well, thanks for working through these problems with me, and thank you for putting in the effort. I appreciate that work that you're doing. Keep it up. The more practice you do, the better you get. You're already great, but I want you to be better, and I believe in you. Good luck on your test. I hope you enjoy it whenever it comes, and let's meet up again sometime in the future. All right. Bye.